Hi guys, Miss O'Connell here. So today we're going to be talking about Hooke's law a little bit more in depth. We'll talk about two more examples and in addition to the graph that we should have populated from our activity on Tuesday. So give this do now a try. So these are three conceptual questions. So what does a larger spring constant mean? So if K is larger, what does that mean? Okay, what implication does that have on Hooke's law? Number two, if there's a negative sign in front of the force, what does that force represent? So thinking about Hooke's law, if that force is negative, what does that negative sign mean? Okay, number three, if an object follows Hooke's law, what type of trend line should we see on a force versus extension graph? So pause the video and give these three questions a try. Okay, so a larger spring constant. If the spring constant is larger, okay, the spring constant represents, we know, the amount of force required to stretch a spring by 1 meter. Okay, so I'm going to write in freehand here because it's very difficult to use these tools on here. F to stretch 1 meter, force to stretch the spring 1 meter. Okay, so if K is larger, the spring is more difficult to stretch or compress. Okay, so with the same amount of force, if K is larger, okay, so if K is larger and F is constant, the amount of displacement that we see will be smaller. Okay, so springs with larger spring constants mean that they're more difficult to stretch. If they're more difficult to stretch, and we apply a consistent amount of force, the amount of displacement that we will see will be less. Another way in which you could have explained this, okay, so you can, if your response is as follows, you do not have to change it, okay, because this is equivalent to what is written on the page. If K is larger, it's going to require more force to stretch the spring. So a larger restoring force would be required in order to get a displacement of X. Okay, so you can either say that larger spring constant at a constant force would mean a smaller displacement, or for a constant displacement, a larger force would be needed if the spring constant is larger. Okay, it's more difficult to stretch a spring that has a larger spring constant. So the restoring force would need to be greater. Okay, number two, if there's a negative sign in front of the force, what does that negative sign mean? Okay, and what does that force represent? So we know that we're talking about a spring on a mass. That stretch, X, which occurs when a spring is at equilibrium and then we add a mass to stretch it to some new rest point. The restoring force will point back towards the equilibrium position. So if F is negative, it represents the restoring force, the force required to return the object back to its equilibrium position. So if F is negative, that means that X would be positive. The displacement would be positive. So if there's a negative sign in front of the force, it is still the restoring force. So that force would represent the restoring force, the force required to return the object back to equilibrium. If the force is negative, that means that the displacement or the compression of the spring must be positive. Okay, so if X is positive, then force would have to be negative, right? The restoring force and the stretch or compression must point in opposite directions. Okay, last conceptual question. If an object follows Hooke's law, what type of trend line should we see on a force versus extension graph? So based on the confirmation or verification activity that we did in class on Tuesday, the force versus compression or stretch graph will be a linear trend line. Okay, so we know that based on the activity, but also if you think about Hooke's law, right, which identifies or expresses how the restoring force, aka in the situation of the verification lab, the force of gravity, right, of those masses is what causes that stretch. The restoring force and the displacement are proportional to each other. Okay, so if they're proportional to each other, that means that a change in one would equate to the change in the other. When you graph two variables that are proportional to each other, the trend line is linear. Okay, because as one constantly increases, the other constantly increases. So the slope will be constant. So we get a linear trend line, and the equation that we can use to model that would be y equals mx plus b. Okay, so let's take this one step further here. So technically, if we take a look at this graph, right, rise over run, the slope of this graph, the rise is the change in the force, the run is the change in the stretch or compression. So the slope is the force, the restoring force, divided by the compression or stretch of the spring. So what would this slope be equal to? If we take the slope of this, what value would we determine? So if you look at Hooke's law, right, if we divide both sides by x, we find that K equals restoring force divided by displacement. So the slope of the force versus stretch graph will give us K, the spring constant of the spring that we are measuring or studying. Okay, so we return from spring break. We're going to go a little bit more depth into we're going to go into a little bit more depth with number 3. So looking at force versus stretch graphs, determining if material is elastic, okay, and determining the spring constant or the rigidness of the spring based on particular systems. Okay, so let's take a look at a few more examples of Hooke's law. So example 2. Okay, so our first example was from the previous video on Tuesday. We're going to talk about example 2 and 3 today. If a 50 Newton force, okay, is required to stretch a spring 5 centimeters. How much will the spring stretch if 125 newtons are applied to the same spring? Okay, so first thing we need to do is identify our givens. So initially, we know that 50 newtons of force, so a restoring force of 50 newtons causes a compression or stretch of 5 centimeters. So this is our initial restoring force and our initial extension of our spring. X must be measured in meters. So we're going to move the decimal place over 2 times. We have 0.05 meters. Okay, so this is what we know. So you have one spring. When we add a mass or force to that spring, it will stretch x1, so initial displacement of 0.5 meters. We then add a larger force or more mass to that spring. We know that force and displacement are proportional. So we know that x2 is going to be larger than x1. But we need to determine how much larger. So when the restoring force is 125 newtons, we need to figure out x2. Question mark. So I'm going to add that to our diagram here. So know that the spring is going to stretch more when we have a larger mass, aka a larger force, added to that spring. We need to figure out this stretch distance from here to here, which would be x2. We know that stretch and extension are related to each other via Hooke's law, which explains that the restoring force is proportional to the stretch or the load applied to a spring. So in order to find the new stretch distance, we must first use, right? We know that if 50 newtons is applied, the stretch or extension is 0.05 meters. So using that information, we can find the spring constant, K. We can find the rigidness of the spring. If we know the rigidness of the spring, we can then find the new extension when more force is applied. So I'll use the information from the first scenario to determine K, and then we will use that K value to find the new stretch distance. So we're going to use Hooke's law, and we're going to plug in using the variables from our first situation. So you have 50 newtons equals K times 0.05 meters. We divide both sides by 0.05 meters to get K by itself. Notice here that that negative sign denotes that the force and displacement are always in opposite directions. When we solve for K, it is a constant. Constants cannot be negative. The stretchiness or rigidness of a spring is not negative. That K or negative sign in front of the K is associated with the displacement. Okay, it gives the direction of the displacement. So when we're solving for K, we omit the negative sign. And we find that the spring constant is 1,000 newtons per meter. So this is a pretty large spring constant. This K would be something used for a type of mechanical machine, maybe found in a car. Okay, the springs that we use in lab would be about 20 newtons per meter. Okay, the spring that you use in your pen would be even smaller. Something as small as 1 or less than 1 newton per meter. Okay, so K has a large variety of values depending on where and when that spring is applied to a system. Okay, so now that we have K, we can use Hooke's law again to determine the new stretch distance. So I'm going to write out the equation for Hooke's law. So this is step 2. We have the restoring force equals negative K times X. Again, that negative sign denotes direction. We're going to take 125 newtons. Set it equal to 1,000 newtons per meter times X, and we'll need to solve for X. So we divide both sides by 1,000. And we find that X is 0.125 meters, meaning 12.5 centimeters. So if you think about that, you need to apply 125 newtons of force to get 12 centimeters of stretch. So that means that this K value is very large. It's going to require a very large force to cause significant amount of stretch. Okay, so that's related to our do now question from 1. When K is larger, it requires more force to stretch the spring. Okay, so let's try another example. So example 3, a spring extends by 10 centimeters when a mass of 100 grams is attached to it. What is this spring constant? Okay, so this example here is the opposite of the example that we talked about on Tuesday. So we're looking at the same variables and the same relationship, okay, but we're basically asked to work backwards here. So we know that we have a spring. Attached to the bottom of that spring is a very, very small mass, right? 100 grams would be 0.1 kilograms. When we add that very small mass the stretch distance, X, is 0.1 meters. Okay, so we always need X in meters, so if you're given centimeters and grams, you must convert. So when we add that 0.1 kilogram mass, the spring stretches 0.1 meters. We need to find the spring constant K. In order to find the spring constant, though, right, using Hooke's law, we know that the restoring force, or the force applied to the spring, must be equal to negative K times X. We're asked to find K. We have X. In order to use Hooke's law, we first need to determine what the restoring force is. So that force that causes stretch is equal to question mark. So if we remember from Tuesday, to determine that restoring force, when we're given the mass, we can use what we know about Newton's second law. Once that mass is applied to the spring, we know that it comes to rest. If it comes to rest, that means that all the forces are balanced. if all the forces are balanced, the sum of the forces in the y are equal to 0. The force that holds the mass up would be the force of the spring. Another force acting on the mass would be the force of gravity, which we know is equal to m times g. So, in order to find the restoring force, we sum the forces in the y. We set them equal to 0 because we know acceleration is 0. We know that the restoring force is positive because it points up. Force of gravity is negative because it points down. Force of gravity is equal to the mass of the object times the acceleration due to gravity on that planet. So we can find the restoring force by simply plugging in m times g. So we're going to plug in mass, we know from above, is 0.1 kilograms. We'll multiply that by 9.8 meters per second squared. Our units will become kilogram meters over seconds squared, which is the definition of a Newton. And we find that the restoring force is 0.98 newtons. What we know about Newton's second law and forces to solve for K. Okay, so step 2, use Hooke's law to solve for K. So let's plug in. So we have 0.98 newtons is equal to negative K times 0.01 meters. Again, remember that negative sign corresponds to the fact that these are in opposite directions. When we solve for K, we omit the negative sign because K is a constant and cannot be negative. So when we solve for K, we get 9.8 newtons per meter. Okay, so significantly smaller spring constant compared to example 2. So this would be a spring that we would see in the lab setting. Okay, so the springs that we would use in lab or in the PhET simulation. Very, very small values for K. Okay, so you're going to head to Google Classroom and try out those few questions in the daily Google form. Have a great spring break. Ha ha ha. Actually stole this from Dr. Grosshandler. He used a similar meme earlier today. So have a great spring break. Okay, you have no work for this course over spring break, but please be back on Monday ready to go. I'm going to attempt starting Tuesday of next week to do live classes. Okay, so make sure that we are aware of that. Okay, and keep your eyes and ears open Monday for directions on how that's going to work. Okay, have a great break.